Okay, so it's time to do the next video. This is the second day of the flat family roof, which was section 9.2.6. Yesterday you had a little bit of homework. Today we'll continue the homework for that section, and then we can check through that tomorrow. Um, so yesterday when we left off, we had built the flat family roof. We had figured out that there are 8 right triangles standing vertically on the roof that hold the guy wires, or that the guy wires are hypotenuses of. And then that was a horrible sentence, by the way. Uh, and then of the 8 triangles, there are only 3 different ones. You can see the yellow one, the red one, and the green one. I'm going to actually be referring to these as small, medium, and large, and you'll see why and when we get some numbers to work with. If we were looking from way up in the sky down on this roof, this is what we would see, and these lines would be the shadows that the wires cast onto the rooftop. So our job today is going to be to figure out how long is each one of these wires and how much total wire does the flat family roof guy have to buy to be able to mount his antenna so that the wires are attached 5 feet below the top of the antenna. It's a 30-foot antenna, which makes the distance from the roof to the connection point 25 feet. So we will be doing this math right now. According to problem 136, the flat family roof is 60 feet long and 32 feet wide. The antenna is 30 feet tall, and the wires are attached 5 feet below the antenna. How long must each guy wire be? Show all your steps to get your solution. So Mr. Flat needs to buy, and then we'll go on to part B after this. So this is 136A. So let's go back to the picture here, and we're going to put the numbers on there: 60 feet wide, 32 feet long, with an antenna that's 30 feet long. Hold on, I got to pause my recording for a minute because I have a cat that's about to attack my work. Okay, I'm back. So the attack cat. For the rooftop here, we're going to make some notations. So we were told, whoa, not that direction. Hold on. We were told that if this antenna is directly in the middle, that this is 32 feet wide and 60 feet long. So I'm going to go ahead and put a little notation here. This is 32 feet and this is 60 feet. And I think I'm going to go ahead and pull the antenna out of the way for a little bit. We can put that back later. Let me move that right up now. Put it up way out of the way. Okay, so in order to figure out how long this diagonal wire is, which is vertical, it's 3-dimensional, it's up above the roof, I really need to figure out the legs of these right triangles. So the yellow right triangle has a leg and a leg, another leg and a leg, and then in the back of this, the green one has a leg and a leg. So we all know the vertical legs, since this is a 30-foot antenna, but they're attached 5 feet below, we can say right now with confidence that the height of this part for all of this is 25 feet. So we have a right angle here, a right angle here, and then one on the green one. What we need to get these diagonal lengths is we need this bottom leg. Well, this bottom leg right here, this is going to be the shadow that we were talking about over here on this picture. So we're going to go ahead and figure out the length of this yellow wire line, the red line, and the green line. Now, as you look at this, we need to be looking for right triangles because right triangles will let us do the Pythagorean theorem. So I'm going to go around this picture a bit. I know that this is 60, which means that each of these yellow halves have to be 30 and 30. if this is 32, the green halves have to be half of 32, which is 16 feet and 16 feet. So now what we're going to do is we're going to figure out the length of this red diagonal. And anytime you're looking for a diagonal length, so like vertical lengths and horizontal lengths can be counted easily, diagonal lengths should be done using the Pythagorean theorem, which means I need to identify a right triangle in this picture. So I'm looking right here. Let's take this yellow one, for example. This is my right triangle. See it right here? So if this is 30 and we know this is 16, I'm going to go ahead and mark that 16 and this 16. In fact, I'm going to mark all the way around this picture so that I don't have to search for numbers. Okay, so in order to figure out the length of the red line, I'm going to call that X for right now. What we're going to do is we're going to do 30 squared plus X squared, plus 16 squared is equal to X squared. So let's see, that's 900 when you square 30. When you square 16, you get 256 is equal to X squared. So X squared, I'm going to flip that around symmetrically, is 1156, which means X is the square root of 1156. I'm not going to bother getting a decimal right now. I'm just going to leave that as the square root of 1156. So here's the square root of 1156. Now, having those numbers is going to help us be able to figure out the lengths, because now we know all of the legs of all of the right triangles. So I'm going to go over here to a place where I can do a little bit more work, and we're going to put along this leg 25. Put those right angles back in the picture. This we know from the previous picture. Sorry. The yellow side is 30, the green side is 16. So I'm going to put a 30 here, and I'm going to put a 16 leg here. And this was the square root of 1156. So now, it's now time to figure out the length of the yellow, the red, and the green. So I'm going to call these small, medium, large, and we'll figure out, because this is the longest one. It goes from the corner all the way over to here. It has the longest distance to span. So let's call this small, medium, and large. And we're going to go ahead and do the math for each of those. Start with the small one. So the leg that's hiding back here on the green is 25. This is 16, and this was my S. So I'm going to say 25 squared plus 16 squared equals S squared. 25 times 25 is 625, plus 256 is equal to S squared. When you add that up, you'll have 800, what's that, 881, 70, 81, yeah, 881 equals S squared. So S is the square root of 881, which is approximately, let's see, 881 square rooted, 29.68 feet. I'm going to make that look a little bit cleaner here. Hold on. So S is approximately 29.68 feet of wire. So this short wire, the green one, this wire is going to be 29.68 feet. The medium wire, if I do the same exact math, 30 squared plus 25 squared equals M squared. So that's 900 plus 625 equals M squared. So I'm going to, let's see, that's 1525 equals M squared. So M is the square root of 1525. I just symmetrically flipped this around and took the square root. So M is going to be approximately, and I get out my calculator. This is where you want to have a calculator. 1525 square rooted 39.05 feet. So M is about 39.05 feet. So we have the small, we have the medium, and now we're going to get the large. And my favorite part about the large one is we're going to actually use this square root without turning it into a decimal. So the large one, 25 squared plus the square root of 1156 squared equals large squared. Don't confuse that L with leg. I'm calling that large. So let's see, this is 625 plus. Now, when you take the square root of a number and then square it, these two operations are undoing each other. So the square root of 1156 squared is just 1156 is equal to L squared. When you add this all up, that would be, what is that, 1781? 56 and 25, 70, 81. Yep, 1781 equals L squared. So L is equal to the square root of 1781. L is approximately 1781 square rooted 42.20 feet. 42.20 feet. So this was problem number, let's go back and double check our math, 9-136A. Let's label this 9-136 part A. So part B, so now we know the length of all three of these. This red one is 42, this red one is 42, this red one is 42, the back red one is 42.2 feet. The small green one, both of them are 29.68 feet, and the yellow ones, both the front and the back one hiding back here, that one is also 39.05 feet. Part B asks, Mr. Flat needs to buy the wire at his local hardware store. He decides to buy an additional 10%. So he's going to have an additional 10% more than the amount that you calculated. So how long must each guy wire be? Okay, so let's see. So we're going to have to calculate his total, it sounds like. Then the amount that you calculated so that he can attach the wires on each end. How much total wire should he buy, including the additional 10%? Show all your work so that Mr. Flat can understand it and round your answer reasonably. All right, here we go. So for part B, let's start with the total. We need 4 of the long ones. So we're going to go 4 times 42.20. Plus, we need 2 of the medium ones, 39.05. Plus 2 of the small, 29.68. And when I figure out what that equals, so let's see here. We need, whoop, your screen sharing paused. I don't want to do that. Hold on. There we go. Okay, so the total amount here, if we take 42.20 times 4, and we add to that 2 times 39.05, and we add to that 2 times 29.68, we get a total of 306.26 feet. So that's about 306.26 feet. But that's before we have the total. So now we need to figure out with 10% more. So if you have 100% of something and then you buy 10% more, that would mean that you have 110% of the original total, 306.26 feet. So the answer he's looking for, he needs to buy 1.10 times 306.26. And if I do that with my calculator, 1.10, 110% of 306.26, I get 336.886. So 336.886 feet. Now they said they want to know how many feet he should buy and round it reasonably. So I don't think he's going to go and get it exactly that length, because he's going to need some extra length. Well, part of that 10% was so that he could tie these off. But if you walk into a store and say, hey, I need 336.886 feet of wire, they're going to think you're crazy. So I would answer it more rounded. I would say he should buy, I don't know, 340 feet, or maybe it comes in bundles of 350 feet. So you could say either one, 340, 350 feet. Maybe I'll say he should buy 340 feet of wire, period. So that's a three-dimensional problem for doing, what do you call this, for doing Pythagorean theorem. Anyway, when you're doing problems where you're calculating diagonal distances, always focus on looking for those right triangles so that you can do leg square plus leg square equals hypotenuse square. Okay, so problem 9-137. This is another 3D version of the Pythagorean theorem problem. A child's shoebox measures 4 inches by 6 inches by 3 inches. What is the longest pencil that you could fit into this box? An empty box may help you visualize the various ways you could fit the pencil in the box. If possible, draw a diagram to show the pencil's position. Show your steps, explore using the 3D model, click and drag the box to rotate it. So we're going to do a different 3D model, but the one in the book is good. If we were going to figure out the longest pencil, we could, if we had a box that looked like this, we could put a pencil, I suppose, inside that box laying sideways. That would be a 3-inch pencil. We could put it standing straight up. There's a 4-inch pencil. Or we could put it this way. There's a 6-inch pencil. But we can get a longer pencil if we go across the bottom, and even a longer pencil if we start here and go up to the corner, kind of like this picture down here. So using that information, we are going to do the, what was that, 3 inches by 4 inches by 6 inches, 4 by 6 by 3. So we're going to do this problem where we're figuring out the length of this green pencil in a box that is that's 3 inches by 4 inches by 6 inches. Now, if you look around this box, hold it, turn it around, you can see that's definitely going to be the longest pencil we can get inside there. Something that's kind of interesting though, so we are looking for right triangles. Well, we need to figure out this length, so this would be a leg because diagonal lengths are hypotenuses. But we're going to find diagonal length in a minute that's actually a leg. So if you look at this box from the top, the shadow cast by the green line would be on the floor of this box. So in order to figure out the green length, we need to figure out the diagonal across the floor. So I'm going to go ahead and draw that segment in here. Right there. And basically what we're doing is we are going to be trying to figure out this right triangle that's in that box. So if this is, let's say, 3 inches, and this is 4 inches, and this is 6 inches. By the way, this is 3-137 that we're working on. To get the problem here, to get this length, I need to look at this right triangle that's sitting on the floor. See this right triangle? So this will be 3 inches, this will be 6 inches, and I'll call this X. This X is our hypotenuse. So my first math is going to say 3 squared plus 6 squared equals X squared. 9 plus 36 equals X squared, so 45 is equal to X squared. That makes X equal to the square root of 45. I'm not going to worry about creating a decimal yet because I may need to square that again in just a moment. So this length is the square root of 45. Going up this side, again like that 4, this is 4 inches. So I'm going to call this distance here, we'll call this one Y. We need to figure out the diagonal length of that pencil that will fit inside of this box if this is the square root of 45 and this is 4. So I could say the square root of 45 squared, because now this is a leg and this is a leg of this right triangle. Square root of 45 squared plus 4 squared equals Y squared. Like the previous problem, the square root of the square of a square root leaves just the radicand. So the square root of 45 squared is 45. Plus 4 squared is 16 equals Y squared. And when you add that up, you get 61 equals Y squared, which means Y is the square root of 61 inches. Now that's the exact answer. The approximate answer, let's see, square root of 61 is between 7 and 8, closer to 8. So we're looking for an answer close to 8 or closer to 8. So let's see, square root of 61 square rooted is 7.81. So it's approximately 7.8 inches. That's the answer to problem 137. Problem number 138 looks like the exact same problem. A fly was sitting on the ground in the back left corner of your classroom. He flew to the ceiling in the opposite corner of the room. How far did he fly if he went in a straight line? Draw a diagram of the classroom complete with measurements. Well, our classroom's not like this. Let's say this was a 30-foot classroom and this was 24 feet wide and the ceiling was 9 feet. How would you figure out how far the fly flew from this corner up to that corner? So this is basically the exact same problem as the pencil. We need to figure out X and then we need to figure out Y. So we could say 30 squared plus 24 squared equals X squared. So let's see, what is 24 squared? 576? Do I have it right? Yeah, 576. So now we get 900 plus 576 equals X squared. 1476 equals X squared. So X must be the square root of 1476 feet. To get the Y value, we're going to take this hypotenuse, which is now going to be a leg in this triangle. See the triangle right here? There's my right triangle. So we're going to say the square root of 1476 squared plus 9 squared equals Y squared. So that gives me 1476 plus 81 equals Y squared. So what's that? 1476 and 81, 7, 15, you're the one, 1557. Is that right? 1557 equals Y squared. So if I do, I'm going to double check my math there because I'm not a real great mental math person. There we go. And then if I take the square root of that, I get 39.46 feet. So y is 39.46 feet that the fly flew from one corner to the next. Okay, so those are a good few examples of three-dimensional Pythagorean theorem problems. Your job is to, for tonight, is to go back and do the angle relationships worksheet. And I want to just double check. Okay, so you have to do the angle relationships worksheet that is linked in Google Classroom. Make sure you show all your work and not just providing answers, and then you can check your answers. I think they're also included. You're looking for things like corresponding angles are equal and alternate interior angles are equal and same side interior angles are supplementary. All those angle relationships we had, the exterior angle theorem, which says the exterior angle equals the sum of the two remote interior angles. There are a lot of different things we've been covering, and it'd be a good idea to start reviewing those. All right, thank you for listening. I hope you're well. Have a good day.